In the last class, we saw how Z and Y feedback could be applied to obtain voltage controlled current source and current controlled voltage source respectively. Then we also discussed how H and G can result in voltage controlled voltage source, that is common collector, and current controlled current source, that is common base structures. Same thing can be done with field effect transistor, single field effect transistor, resulting in common drain and common gate configurations. We are now discussing how H and G feedback can be applied using a pair of transistors, cascaded amplifiers, that is a transistor amplifier, let us say bipolar or field effect. AC picture only is given, cascaded to another transistor amplifier. So, we have T1 and T2 with respective loads RC1 and RC2. So, one amplifier is cascaded to another amplifier. When such a pair, okay, as shown here is used, what are the possible negative feedback configurations? I have told you earlier that with a single transistor and additional passive network, you can only get negative feedback structures which are Z and Y. Without any passive network, you can get H and G. With a pair of transistors like this, you will get negative feedback only for H and G feedback. What is H? It is series at the input and shunt at the output. G feedback is shunt at the input and series at the output. H feedback is adopted in order to obtain a voltage controlled voltage source. So, H feedback is adopted for an idealization towards voltage controlled voltage source. G feedback for an idealization towards current controlled current source. So, how are we therefore to implement this H feedback? It is shunt at the output and series at the input. That means, I take a feedback network, this is the passive feedback network, I develop, this is let us say R1 and this is R2. This is the passive feedback network. The output voltage is sampled here V0 and V0 into R1 by R1 plus R2, V0 into R1 by R1 plus R2, that is the amount of feedback voltage. That is going to be put in series with the original input. The original input of the amplifier is this, right. This is the feedback voltage. So, we are going to lift this and put it in series. From here to here the phase shift is 180 degrees. From here to here again the phase shift is 180 degrees, and therefore, from here to here the output and input voltages are in phase. Therefore, this voltage and this voltage, they are in phase. That is why, if I now apply in this in series with this for the new input, these two will be coming in series and this feedback voltage will be opposing the input voltage. That is why it is negative feedback. So, this is the H feedback, and obviously H parameter is most suited for analyzing this. Therefore, we will write the composite H parameters for this. This is the method we have been adopting throughout. Composite parameters will determine for this whole network. How do we determine composite H parameter? So, Hi of this network, this is Vi now, Hi of the network is going to be Hi of the amplifier plus Hi of the feedback network when the output is shorted, because it is a short circuit parameter. Now, you can see when the output is shorted, the feedback comes out of this amplifier, right. These two now get separated, and R1 will come in parallel with R2 here at the input. So, R1 comes in parallel with R2 at the input of this amplifier T1, and therefore, the input impedance of this network is going to be Re of this plus R1 parallel R2 Re1 plus R1 parallel R2 into beta plus 1. It is because we are looking at the base, the current here is beta plus 1. So, any impedance coming in series, that is Re1 in series with R1 parallel R2 is what comes, that into beta plus 1 is now Hi of the composite amplifier. You can see that of the amplifier is Re1 into beta plus 1, that due to the feedback network is R1 parallel R2, since it is coming in series with the emitter, not in series with the base, we have this beta plus 1 factor coming into picture. So, you will see that the H parameters add. Next, we can simultaneously determine Hf of the composite structure, which is again Hf of the amplifier, okay, plus Hf of the feedback network. When what is Hf? I short the output and find out the current gain from input to output. When I have an input current I, this current at this point is going to be beta times II, that we know. This beta times II is going to split between this resistance and the impedance seen from here. Impedance seen from here, so the current gain is one value is beta straight away, from here to here there is a gain of beta. Then the current is going to split between this resistance and the resistance seen from here. The resistance seen from here is Re2 of this into beta plus 1. So, it is going to get reduced by Rc1 by Rc1 plus Re2 into beta plus 1. That is the current that is going to be pumped into this in this direction. This is the current now. That is again going to be beta multiplied here, beta times that is the current here. So, we get beta squared. This current we have come to, okay, and this current is going to be totally going into this, because this is short. So, this will be totally going into this in this direction. So, when this is going like this current is coming like this will come like this, and therefore, this will go like this, and therefore, the current gain is negative. Now, look at this current here. If II is here, the current in this is beta plus 1 times II, out of which portion of the current gets added to this, right. So, the direction is in the same manner. So, minus R1 by R1 plus R2 times beta plus 1 times II. So, this contribution is due to the feedback network, this contribution is due to the amplifier, it is dominant. You can see beta squared appearing here. So, this may be negligible, okay, because there is an attenuation and just only beta plus 1 here. Now, that part is over. H I amplifier, H F that is H I composite, H F composite, these are evaluated. Now, we have to evaluate the other two parameters. That we make this open circuit and apply a voltage here, V naught. So, V naught, when you apply here, there is no current in this, and therefore, the voltage here is going to be V naught R 1 by R 1 plus R 2 just. So, there is no current here. So, this voltage is going to appear as the open circuit voltage here. So, this is H R, the feedback voltage from output to input when the input is open is simply R 1 by R 1 plus R 2 times V naught. So, this is H R, very simple. Then the output impedance is V naught by I naught here. So, there is R C 2 shunting this, nothing is happening, this is 0, this is 0. So, these things are ineffective. So, R C 2 is shunting R 1 plus R 2. So, 1 over R C 2 plus 1 over R 1 plus R 2. So, that is essentially the output conductance. So, the composite H parameter is very simply evaluated just by looking at the circuit. These are the open circuit parameters, these are the short circuit parameters. And you can see that amplifier does not contribute to the feedback, only the passive network contributes to the feedback. Here this is the output conductance of the amplifier, this is the conductance of the feedback network. So, the loop gain. Since this is beta squared here, right, this factor we are going to ignore, let us say this is neglected, very small, neglected because this is beta squared. Okay. Here all can become comparable except RE 1 here, which is very small compared to R 1 parallel R 2 normally. So, we have simplified these parameters now. These parameters will establish the loop gain as negative here. So, this is negative feedback. This into this divided by this into this is the loop gain. So, minus beta squared, okay, into R 1 by R 1 plus R 2 into R C 1 by R C 1 plus R E 2 into beta plus 1, that divided by R 1 parallel R 2 into beta plus 1, okay, this into 1 over R C 2, 1 over R 1 plus R 2. As long as this is much greater than 1, there is good negative feedback here, and therefore, it is a good negative feedback structure, and therefore, it will result in a good voltage controlled voltage source. Now, we can once again establish after feedback what the input impedance, output impedance and forward transfer voltage gain is going to be for this. Now, obviously, the parameter of interest will be the G parameter of the structure, and in the G parameter we can establish that the forward transfer voltage gain has to be determined by only the passive network. The feedback factor is R 1 by R 1 plus R 2, and the gain has to be 1 over the feedback factor. That is what we have established if the loop gain is very high compared to 1. So, the gain of this structure has to become, okay, G F. is going to be very close to 1 plus R2 over R1, just the inverse of this feedback factor, 1 over R1 by R1 plus R2 or 1 plus R2 over R1 should be the thing, and these two, that is G I and G naught, should go towards 0. G I, G R, G naught, all the other three should go towards 0. That we can very clearly establish. The G F is nothing but plus this factor divided by the matrix here, this into this plus this into this. We will do this for a numerical example and show that G F will go towards always 1 plus R2 over R1 if this loop gain is magnitude of loop gain. This is negative for negative feedback, and the magnitude of loop gain, if it is much greater than 1, then this goes towards 0. So, it reaches an idealized voltage controlled voltage source. So, the output impedance should go towards 0 because it is a voltage source. Input impedance should go towards infinity, or input conductance also should go towards 0, right. So, G I and G naught and G R, all these things will be going towards 0. So, you can establish that this G parameter in fact becomes extremely small if this loop gain is very high. So, let us now consider an example in this H feedback, example 3. This is the feedback amplifier. Now, we have a source with 100 K source impedance and a load of 10 K. So, this is the practical situation. This circuit is the AC picture of the feedback amplifier network. Beta of the transistor equal to 200, and these two transistors are made to operate at a current of 0.5 milliamperes, with the resultant effect RE1 equal to RE2 equal to roughly equal to 50 ohms. That is 25 divided by 0.5 ohms. So, 50 ohms. So, the input impedance of both these will be 50 into RE into beta plus 1, we will assume it as about 200 itself, which is about 10 K. So, this is offering 10 K, here also RE into beta plus 1 is roughly equal to 10 K. For ease of calculation, these have been adjusted to be so, right, because the load resistance also is 10 K. Now, let us write down the composite H parameter straight away. Once again, this will illustrate clearly how to go about writing down the composite H parameter just by observation. Once again, we short circuit this. So, the composite H parameter of this network now has to take into account both source and the load impedance. Okay. So, we have at the input 100 K source impedance plus obviously the 10 K, which is RE1 into beta plus 1 roughly equal to 10 K, plus then this is shorted, we have 20 K parallel 20 K, which is again going to lead to 10 K. So, once again we have the source resistance coming in series with this impedance, right, 100 K into plus RE1 into beta plus 1 plus R1 parallel R2 into beta plus 1. Right. So, this 10 K into beta plus 1, which is again 201, or you can put it there. So, this is the input impedance of the network, RE1 into beta plus 1, this into beta plus 1. Okay. So, we have here now again current gain equal to beta 200, another beta here 200 square, and this being short circuited, it will go there. Here there is a current division, this is 10 k and this is 10 k. So, current division is by half. The current here, which is beta times II, is going to split between this and this equally, because the input resistance is 10 k. So, these two parameters are easily evaluated. Then open circuit this, okay, and find out the output parameters. When you open circuit and apply V naught here, the feedback factor is half 20 k by 20 plus 20 k, which is half, and the impedance here is 1 over 10 k, this shunted by 40 k plus of course this load resistance, which is 1 over 10 k. So, total admittance at this node, this 10 k 1 over 10 k, this 1 over 40 k, this 1 over 10 k, total admittance. Here it is total impedance, here it is total admittance. So, that is all. This is the composite H parameter, right. So, basically let us evaluate this. This is going to be 10, this is going to be 20, 20, 10 k, right. So, 2020, 2120 k. So, this is pretty high, you can see already. Then we have this as 0.5, this is 4 into 10 to power 4 by 2. So, 2 into 10 to power 4. The other factor due to this, which is beta plus 1, okay, into half, is going to be ignored here. This is going to be added to this 2 into 10 to the power 4, okay, plus this with this negative sign, right, minus 200 by 2, 100, a factor of 100 we are ignoring here. So, now the loop gain is minus 2 into 10 to the power 4 into 0.5 by 2120, okay, k. So, into 10 to the power 3, this is going to give you 10 to the power minus 3. So, that gets cancelled into 1 over 10 plus 1 over 40 plus 1 over 10. Okay. Strictly speaking, therefore, it is 2 over 10 or 8 over 40, right. So, 9 over 40. Two over 10, okay, or 8 over 40, 8 plus 1, 9 over 40, k getting cancelled with this k. So, this is strictly into 10 to the power minus 3. So, we see here this is getting cancelled with this, right. This is cancelled with this, and therefore, we have this as 4 into 10 to the power 4 by right. So, 1908, about 2000, right. So, this is really equal to roughly 2000, okay. So, approximately equal to minus 2 into 0, right, 20, much greater than 1. So, the loop gain is much greater than 1, no problem. Therefore, we can go ahead with evaluation of G parameter now to establish that this is resulting in a very good voltage controlled voltage source. For us to obtain the G parameter, it is, let us find out delta H here, which is this into this, which is 2120 into 9 over 40, that is that factor, okay, plus, okay, 10 to power 4. So, this we had once again so 10 to power 4 plus something like that, right. So, 10,000 about 500, okay, 477. So, essentially 10 to power 4 dominates, okay. We therefore, now establish the G parameter simply by here G f is 2 into 10 to power 4 by this 10,477, which is very nearly equal to 2, right. So, this is very nearly equal to 2, slightly less than 2, okay. You can see that is what has happened. We had a feedback factor of 0.5, 1 over 0.5 is what is going to appear as GF, 1 over 0.5, 2. That is purely determined by these two passive resistances 20 K and 20 K. Nice. Now, let us find out GI. GI is this factor divided by this. Let us say we will approximate this as 10 to the power 4 already, right. So, this factor, which is 9 by 40 into 10 to the power minus 3 divided by 10 to the power 4. So, 10 to the power minus 7, see it goes towards 0. What is it actually? It is nothing but input impedance, okay, which is 40 by 9 into 10 to the power 7 ohms or 400 by 9 mega ohms. This is the kind of input impedance that this feedback amplifier has given you, 400 by 9 mega ohms. So, it has become almost an open circuit. Next, let us see what is the output impedance. That is going to be given by G naught, which is this divided by 10 to the power 4. Which is going to be 212 ohms. So, even though we have had an amplifier which uses 10 K and parallel with 40 K and 10 K etc., we have now got an output impedance which is of the order of 212 ohms, pretty low. Okay. So, the output impedance is going towards 0, okay. Input impedance is going towards infinity, or input conductance is also going towards 0, and this factor obviously is minus 0.5 divided by 10 to the power 4. So, that also has gone towards 0, 0.5 into 10 to the power minus 4 or 5 into 10 to the power minus 5. So, all these factors are going towards 0. So, this is the important conclusion that we are arriving at when we design a practical voltage controlled voltage source. Now, this input impedance involves this 100K source resistance. So, if you want input impedance of the amplifier without source resistance, you have to take away 100K from this. So, that is very simple, right. This is of the order of mega ohm, taking away 100K is not going to influence it much. Similarly, if you want the true output impedance, you have to take away the shunting effect of the load resistance 10K from this. Right. So, that is also very simple. 212 is the output resistance, and 10K is not going to cause much of a difference in the output impedance, even if you take away. So, it is nearly going to remain as the same value. So, we have now seen how we can design a good voltage controlled voltage source with stable gain, with high input impedance and low output impedance. We just saw how H feedback results in idealized voltage controlled voltage source. Now, the dual of that is G feedback, that should result in current controlled current source. Now, we once again take the cascaded amplifier T1, amplifier T1 with collector load of RC1 is cascaded to amplifier T2 with collector load of RC2, and then we say it is current controlled, that means input impedance should come down, current source, output impedance should go up. Things should be in shunt at the output. So, this is the feedback network, it is in shunt at the output, common, right, voltage is common to both, and in series with at the input. That means, I lift this and connect it together, lift it and connect it together in series. So, the output current is common to both, right here for the feedback network and now. So, the feedback network remains the same, R2 and R1. The current here is going to be taken and is going to get divided based on this kind of relationship here between R1 and R2. So, G parameters have to be chosen, which means you open circuit the input and open circuit the output and short circuit the input for obtaining the respective G parameters, and evaluate Gi composite G parameters have to be determined. You open the output, measure the input conductance which is due to the amplifier as well as the feedback network, and then short the input and measure the feedback factor here. If you short, the output current is going to be split between R2 and R1, and therefore, the feedback factor once again is going to be divided by R2 plus R1. Okay. So, there is going to be feedback factor only determined by the passive network, and output conductance also can be evaluated here. Ultimately, you must have, since the feedback factor here is R2 by R2 plus R1, that current at the output is going to be divided between this resistance, this is already shorted here. So, R2 by R2 plus R1 is what is fed back as the current. So, this is the feedback factor, and therefore, 1 over this is the current gain. So, you have to obtain the composite H parameter or HF from the composite G. So, then it will be 1 over this as the gain, 1 plus R1 over. That will be the current gain from here to here. and what happens to the input impedance? It comes down. Output impedance should go up. Or in the H parameter, H I, H R and H O, all these three things should go towards 0. Only H F should get stabilized at a value of 1 plus R 1 over R 2. I am going to leave this as an exercise for you, just as we did in the case of H parameter. Please find out the composite G parameter here. In the H feedback, we found out the composite H parameter and then converted into H. Here, find out the composite G and convert it into H, and establish that the current gain is 1 plus R 1 over R 2. Now, this completes essentially realization of all the idealized sources. Now, there is another way of obtaining voltage controlled voltage source and current controlled current source. These are not really basic sources, as I had mentioned about this in the first part of my lecture, right. You can obtain voltage controlled voltage source and current controlled current source by cascading voltage controlled current source cascaded with current controlled voltage source will give you voltage controlled voltage source. Current controlled currents, that is current controlled voltage source cascaded with voltage controlled current source will give you current controlled current source, right. So, this results in voltage controlled voltage source, this results in current controlled current source. So, if you are able to develop good voltage controlled current source and good current controlled voltage source, that is sufficient. You can realize all the idealized sources, that is voltage controlled voltage source, current controlled current source, current controlled voltage source, voltage controlled current source. Whereas, if you realize good voltage controlled voltage source and current controlled current source, you cannot realize the other two sources by simple cascading. So, these are basic sources, current controlled voltage source and voltage controlled current sources, these are basic sources. If you realize this, then by cascading we can realize this. So, we know that, for example, by giving Z feedback, this is Z feedback, we are able to realize voltage controlled current source. This we had discussed in the last class. By giving Y feedback, we are realizing current controlled voltage source. And now, if I cascade this, right, at the input it is voltage controlled, at the output it is a voltage source. So, I am going to realize this cascaded together, right, is going to realize a voltage controlled voltage source of gain. Now, let us see. If I apply V I, this V I is going to result in a current of V I by R E approximately, because this small r e is going to drop very little. So, this current is going to be emitter current, this current is going to be collector current almost nearly alpha times that. So, this is also V I by R E. If this is V I by R E here, right, we have seen in our earlier this thing that this whole of this current is going to flow through R F only and result in a potential here plus minus of V naught is equal to R F into V I by R E. So, you get a voltage gain of RF over RE. So, suppose RF is 10 k and RE is 1 k, you are now designing a nice voltage controlled voltage source of gain equal to 10 without taking recourse to the H feedback with the pair that we had earlier discussed. Similarly, you say okay, I want a current controlled current source, not this, then what you do is simply put this first, RF. So, put this first, current controlled voltage source is put first and then you put this later. Now, once again, if this is II, okay, the voltage that is developed here, all this current will go through this as II into RF. So, the voltage is okay, II into RF this way, this is minus and this is plus. This voltage is very nearly 0, right. So, the output voltage is II into RF and this is going to result in, okay, this is plus and that is minus. So, a current in this direction of II RF divided by RE. So, the current will come out, okay, II RF divided by. So, output current is going to be II RF by RE. Once again, if I pump a current here, this is going to establish a potential here plus minus this way, minus here, minus plus here. This will force a current in this direction, this voltage, okay, which is II RF divided by RE, and therefore, output current I naught is going to be II RF by RE. So, you have now established a current controlled current source here with a gain of RF over RE. So, you see these two networks are not networks with overall feedback. Here this current controlled current source has overall feedback. Two transistor amplifiers are cascaded first and then the output current is fed back to the input using this network. Here it is not done that way, these have local feedback. Two local feedback structures are coupled together, right. So, that is the difference between this structure and this structure. This local feedback and overall feedback have their own advantages and disadvantages. Obviously, the first advantage here, which is very clear, is that since you are cascading two amplifiers, the loop gain is always going to increase, right, compared to one amplifier. So, the loop gain of more number of stages will always be higher than the loop gain of less number of stages, that is obvious. So, the sensitivity to active parameter is going to be less in overall feedback structures compared to local feedback structures where the loop gain is just that of the individual stage. So, the sensitivity to active parameter is going to be more here, but we will later see that there is a great advantage in local feedback in terms of trouble free operation at high frequencies, because as you increase the number of stages we get into the problem of oscillations. Negative feedback turns itself into positive feedback beyond a certain frequency and the circuit, instead of amplifying, is going to oscillate. This we will later on discuss. So, it is not always advantageous to simply cascade amplifiers and then give overall negative feedback. As you cascade amplifiers, the individual time constants will cause a delay in the whole structure, and what you are considering as negative feedback will turn, the phase shift will change in such a manner that what you consider negative feedback at a certain frequency will turn itself into positive feedback, and that is a danger. The positive feedback with loop gain greater than 1 will cause what is called as instability in amplifiers or oscillations. Okay. So, this kind of configuration for more than two pairs is definitely dangerous, right. This pair gives you problems if the loop gain is pretty high. But if you add one more stage of amplifier, it make it a triple instead of a pair, then definitely it is rare that such a circuit straight away works without what is called frequency compensation. Right. We will discuss these effects of high frequency and effect of delay in the individual stages at a later point. That is also very important. So, we always restrict our operation if possible to 2 stages. When we go to 3 stages, we encounter several problems, okay, in the operation of the amplifier satisfactorily. So, overall feedback is mainly restricted to 2 stages, right. Under rare cases one can go to 3 stages, but then there will be bound to be problem. Okay. Now, therefore, we have discussed almost all negative feedback structures using transistors. Same thing can be discussed using field instead of bipolar junction transistors, we can replace them with FETs. The same analysis is valid, same conclusions will also be valid. Okay. So, we are not going to do this, except that maybe at a later stage we will work out certain problems with FETs being used. Okay. I would like to at this juncture bring in the operational amplifier that we have already managed to construct. Operational amplifier is nothing but a control source with forward transfer parameter being very high. It could be voltage controlled voltage source, current controlled current source, voltage controlled current source or current controlled voltage source. Any of the 4 categories can become operational amplifiers. The conventional operational amplifier, which is very popular like that of 741 or 747, is a voltage operational voltage amplifier. That means, it is a voltage controlled voltage source with what kind of parameters we are talking of? H parameter ideally. This is 0, this is 0, this is 0. Okay. Sorry, this is a voltage controlled voltage source. G parameter, Gi is 0, Gr is 0, G naught is 0, Gf okay, is going towards infinity. If it is a current controlled current source or a current operational amplifier, then you have H parameter of concern. This is 0, this is 0, this is 0, and Hf goes towards infinity. If it is a transconductor type of amplifier, okay, then the Y parameters are the ones that have to be taken, which is 0, 0, 0, and Yf goes towards infinity. If it is transresistor type of amplifier, that is the Z parameter is what is talked about, and here this is 0, this is 0, and this is 0, and it is Zf which goes towards infinity. So, these are the 4 types of op amps which can be made available. This is the popular one. Okay. These are becoming popular now, okay. And therefore, it is necessary to know that one could use any one of these 4 and still come up with applications of the same type. Okay. So, we will discuss this in the next class, how to design negative feedback configurations using operational voltage amplifiers. That will be the topic of the next class.